Now let us see the definition of eigenspace. Yesterday, I think we have already seen the definition of eigenspace before. Last time we have seen the theorem that eigenvectors corresponding to distinct eigenvalues are linearly independent. Now let us see what is an eigenspace. So let A be a square matrix obviously, and lambda be an eigenvalue of A. Then the set of all vectors which satisfies the equation Ax is equal to lambda x. Remember, together with the 0 vector, this is important, is called as eigenspace of A corresponding to eigenvalue lambda, and it is denoted by E of lambda, or sometimes it is also denoted by E of A lambda. That is nothing but E of lambda is set of all x belonging to R raised to n such that Ax is equal to lambda x. So by simple calculations, if you shift Ax on the right hand side, you will get lambda x minus Ax will be equal to 0, and over here we can introduce I. So it is same as lambda ix minus Ax is equal to 0, and if you take x out, you will get lambda I minus A outside the bracket x is equal to 0. So remember, this is nothing but our eigenspace. In short, eigenspace is nothing but what? It is a collection of all vectors x belonging to R raised to n satisfying this system. Actually, it is nothing but what? It is a homogeneous system, isn't it? And remember, if order of the matrix is n, then you are having this x belongs to what? R raised to n. So if you are having a 3 by 3 matrix, then this x will belong where? To R raised to 3. Okay, this is supposed to be understood. So actually, finding the eigenspace is nothing but finding what? The solution of the system, the homogeneous system, in fact, isn't it? And which homogeneous system? Lambda I minus A outside the bracket x is equal to 0, where lambda is nothing but what? Eigenvalue. So if your matrix is having 3 eigenvalues 1, 2, 3, so corresponding to each eigenvalue you can find the eigenspace, and they will be E of 1, E of 2, and E of 3. And what will be your E of 1 eigenspace? It will be collection of all those vectors belonging to R raised to 3 such that if you have to put lambda is equal to 1, so it will be I minus A outside the bracket x is equal to 0. Now A is also known to you, I is also known, so simply find I minus A, you will get some matrix over there, and the notation used for capital X I am going to use xyz, the column vector xyz, isn't it? Like this, then you will get one homogeneous system. Simply solve that homogeneous system, and that is going to give you the eigenspace. So now this is regarding eigenspace. Now the question is, what do you mean by eigenvectors? So the basis of eigenspace are basically nothing but what? Eigenvectors. So as we have already seen before, that this eigenspace is nothing but a subspace of R raised to n. Since it is a subspace, definitely it is going to have some basis, and that basis is nothing but what? The eigenvectors. Okay. And let us go for a few examples. So in these examples, we have to find the eigenvalues and the basis of the corresponding eigenspaces for the following matrices. So first of all, the simple matrix 1, 2, 3, and 2. I will give it a notation. I will select A is equal to 1, 2, 3, 2. And we know the characteristic equation is given by, so we have, I will say, first of all we'll find eigenspaces, and from that eigenspaces we'll find basis of the eigenspace, and once we get the basis of the eigenspace, we'll get what? The eigenvectors. So first of all, to find, directly I'll write eigenvectors. So in order to find eigenvectors, we are supposed to write down the eigenspace. So I'll say we have, what is our eigenspace? E of lambda is equal to, now since it is a 2 by 2 matrix, it will be a collection of elements from R2 such that lambda I minus A outside the bracket x will be equal to what? 0, as an eigenspace corresponding to eigenvalue lambda. Now I will take one vector from this eigenspace. Okay, so I'll say let x is equal to, the notation I am going to use is xy. belongs to E of lambda be any element, so that it will be easier for us to do the calculation. That's it, be any element. Therefore what will happen, this lambda I minus a outside x will be equal to 0. This will imply what will be lambda I? Lambda I will be lambda 0 0 lambda, it is I2 actually, right? Minus, and what is my A matrix? 1 2 3 2. Then outside it is xy will be equal to, and this is nothing but a 0 matrix, a column 0 matrix actually, a column vector rather. And if you simplify it, this implies it will be lambda minus 1 minus 2 minus 3, and it will be lambda minus 2 outside the bracket xy will be equal to what? 0. I'll call it as some star. Now one by one we'll find the eigenvectors. I'll say for lambda is equal to minus 1. So for lambda is equal to minus 1, the idea is simple. Put lambda is equal to minus 1 in star. Put lambda is equal to minus 1 in star. Therefore what you are going to get, you will get one system. So minus 1 will be minus 2 minus 2 minus 3, and it will be minus 3 outside the bracket xy will be equal to what? 0 comma 0. Now you have to solve this system. So there are many ways to solve it. Okay, so I will consider the augmented matrix. So what is our augmented matrix? So augmented matrix is nothing but what? minus 2 minus 2. किंवा इथे डायरेक्टली सॉल्व केलं असतं तरी चाललं असतं, but doesn't matter. We'll consider the augmented matrix 0 0. Now I'll say by minus 1 upon 2 r2 and minus 1 upon 3 r3. So by performing these operations you are going to get 1 1 1 1 over here 0 0, still not in echelon form. So I'll perform r2 minus r1 operation. Now you'll get the echelon form. So this will be equivalent to 1 1 0 0, and it's going to be 0 0. Okay, so what is your equivalent system? Okay, so equivalent system is, okay, but first of all I'll write down the rank. Therefore your rank over here is equal to 1, which is less than 2, which is number of unknowns. So how many parameters? Therefore number of parameters that we are going to use here is 1. Okay, so I'll write down the equivalent system. Equivalent system is, so what is the equivalent system? It is x plus y is equal to what? 0. So you can put parameter to any one variable. So I'll put y is equal to t, where t belongs to r. Therefore what will be x will be minus t. Okay, so therefore what will be your eigenspace? Therefore our eigenspace E of minus 1 is equal to set of all. What notation we have used for capital X? It is x comma y, right? So set of all xy rather. Okay, so set of all xy such that, where it is I will show you. We'll go back. Yeah, here it is, isn't it? This is the notation used for capital X, and this is what will be your E of 1 actually. It will be set of all x, but the notation used is xy. So set of all xy such that we got the values of x and y now. X is equal to minus t, and y is equal to what? T, where this t is belonging to r. Alright, I will write it outside. Yeah, where this t belongs to r. So therefore this is equal to, put the values of x and y. So it is nothing but set of all minus t such that this t belongs to r. Now you pull this t out, so you get minus 1 1 such that t belongs to r. So you got the eigenspace. So this is your eigenspace corresponding to eigenvalue minus 1. So therefore what is the basis? Therefore the set 1 minus 1 1 is a basis, don't say the basis, okay, is the basis of this eigenspace E of minus 1. Therefore what is the eigenvector? A basis, uh, whatever the basis of eigenspace is there, that is nothing but eigenvectors. Basis in the sense the the vectors in the basis set, that are nothing but eigenvectors. So which vector is present in the basis set? That is column vector minus 1 1. So that is nothing but our eigenvector. So therefore I'll say minus 1 1 is an eigenvector, okay, is an eigenvector corresponding to, I am saying an eigenvector, not the eigenvector. Keep it in mind, eigenvector is not unique, is an eigenvector corresponding to eigenvalue minus 1. Okay, was easy, right? So I'll leave the rest, the other part for homework. For lambda is equal to, the eigenvalue was 4. Okay, so this part is homework. You send me the solution on